Okay, good morning, everyone. All right, so we're going to get started. We're going to continue from our previous lecture on randomized distributed algorithms. Okay. So we were looking at this problem called distributed maximal independent set. Right? And remember, the problem is that we're given this graph, and then we want to find a subset of the nodes where all of these nodes are not connected to each other. Okay, so for example, these three red nodes over here are not connected to each other. Okay. And then we want to make this set be as large as possible. Right, so so for example, you can see that in this graph, if you add in any other node, right, if you take any of these other blue nodes and if you try to add it into the set, then it's not going to be independent anymore. Right, so for example, if you add this one, right, then it's going to be connected to one of these red nodes. If you add this node, right, it'll be connected to this node over here. Okay. So we're trying to compute a maximal independent set, and we want to do this as quickly as possible in a distributed fashion. Okay. So sequentially, it's easy to do this in linear time. Okay, but in a distributed setting, we allow all of the nodes to work together. So it's possible that we can go in faster than linear time. Right, so then the algorithm we're going to look at is, well, first of all, the model that we're going to use, okay, is going to be called the synchronous round model. Okay, so basically what happens is we imagine that you can divide time into these discrete blocks. Okay, so each block is like a round. And then within each round, we allow all of the nodes to do something. So in particular, we allow all of the nodes to broadcast a message to all of its neighbors. Okay, so each node has a bunch of neighbors, and in every round, you allow the node to broadcast a message to all of its neighbors, and all these neighbors get that message. Okay, now remember that previously we said in these distributed networks, oftentimes it's hard to broadcast a message, because if two nodes broadcast a message at the same time, then these broadcasts can interfere with each other. Okay, but now here, we're assuming that every round, a node can broadcast a message. Okay. And the reason we're making this assumption is because last time we looked at this algorithm for contention resolution, which basically allows a group of nodes to all send messages to each other. Right? But that took several rounds to complete. It took basically a logarithmic number of rounds to complete. Okay, in the previous contention resolution problem. Okay. Now, in this new problem, in the MIS problem, okay, we're just going to use the contention resolution algorithm as a subroutine. Okay, and we're going to treat all of the time that you spend for the contention resolution, which is basically order log n rounds. Okay, we're going to treat that as a single, let's call it super round. Okay, we're going to treat all of that, all of those log n rounds as one big round. And so within one big round, all of the nodes, which are neighbors of each other, can send a message to each other. Okay, so this MIS algorithm is going to use the previous algorithm as a subroutine. Okay, all right. So so then what is the algorithm? The algorithm is quite simple. Okay, so what we want to do is to make sure that if one node chooses to enter the MIS, then all of its neighbors do not enter the MIS. Right. That's how we can preserve independence. Okay, so then what we're going to do is every node in each round is going to choose a random number, okay, between 0 to 1. And it's going to send it to all its neighbors. Okay, and then next, if you have a node, R of V, V, okay, and R of V is a value that V selects, right? It's a random value. Okay, so V's value is less than the values of all of its neighbors. Okay, so V is like the minimum among all its neighbors. Okay, then V is going to add itself into the MIS. Okay, furthermore, it's going to tell all its neighbors that it added itself to the MIS. Okay, all right, and then after that, if either V or one of its neighbors entered the MIS, right? So for example, if V has a minimum value, it's going to enter the MIS. Okay, but then V is also going to tell all its neighbors that V entered the MIS. So therefore, if either you have the minimum value, or if one of your neighbors said that they have the minimum value, okay, then you're going to terminate. Okay, and when you terminate, you remove all of your neighboring edges. Okay, so as an example of this, suppose you have suppose this node over here. Okay, suppose this guy actually has the minimum value. Okay, then he's going to broadcast this information to all his neighbors, right? So he's got 3 neighbors over here, and then all of these neighbors are going to terminate execution. Okay, and when they terminate, they're also going to remove all of their edges. Okay, so this guy, yeah, so we're going to remove all of these edges here. Okay, so this guy is V over here, who has the minimum value, right? He tells all his neighbors to terminate, and when all of these guys terminate, they're going to remove all of the edges which are connected to them. Okay, yeah, and otherwise, if you didn't get a message from any of your neighbors, okay, then you just go back to the first step and you just keep repeating this. You pick another random number, and then if you happen to be minimum, you're going to enter the MIS and also tell all your neighbors. And yeah, and if actually one of your neighbors told you that they enter the MIS, then you're going to terminate and take out all of your edges. Okay, so you just keep doing this until eventually the whole process terminates. Okay, so so we're going to take so basically we're repeating these 3 steps over and over. Okay, and we're going to call these 3 steps a phase. And then later on, we're going to analyze how many phases we're going to do before we terminate. Okay, now let's make a simplifying assumption, which is that when you select these random numbers over here, you never have any ties. Okay, so yeah, and you can do that just by selecting like a real random number. Okay, instead of like you know, some sort of fractional number. Let's say you select a real number, and then it's very unlikely that you get a tie. Right? Or alternatively, you could also like append the number that you select with your node ID. Okay, and then you can compare this sort of pair of numbers lexicographically, and that way you would never have any ties. Okay, but in any case, it's easy to ensure that there are no ties, and so we're just going to assume that. Okay, any questions about this algorithm? All right, so let's first of all show that this algorithm works correctly. Okay, in other words, it actually does output a maximal independent set. And then later, we're going to show that it works quickly. Okay. Okay, so first of all, we claim the output is actually an independent set. And this is because, you know, for every 2 neighbors, you know, only one of them is going to have the smaller value. Okay, so you're only going to join the MIS if you have the smallest value among all your neighbors. So it's impossible for 2 nodes to both, 2 neighboring nodes to both join the MIS. Okay, yeah, and then also, as soon as one node joins the MIS, then it's going to remove all of its neighbors. Right, all of the neighbors are going to hear about. Are going to hear this message, and then they're going to terminate. Okay, so therefore, in the end, we're never going to have 2 neighbors which are both in the MIS. Okay, so this shows that the output is actually an independent set. Right, and then next, we need to show that it's a maximal independent set, and this is true because the only time that you ever take out a node is if either the node itself is in the MIS or one of its neighbors is in the MIS. Right. So in both cases, you know, the node that you take out cannot be in the MIS. So the only nodes that you ever remove are the nodes which are guaranteed cannot be in the MIS. Okay. And so therefore, in the end, what you end up with is a maximal independent set, because you never take out nodes which can possibly still be in the independent set. Okay, so yeah, so that shows that we produce an MIS in the end. Okay, so the next question is how you know, how fast does this work, right? How many phases or rounds does this take? Okay, so to show this, the main lemma we're gonna try to prove is that in each of these phases. So remember, the phase has basically these you know, 3 steps. We're gonna call this a phase, right? These 3 steps over here. Okay. All right, so we're going to show that for in each phase, at least half of the edges are removed in expectation. Okay, so in each phase, you know, some nodes join the MIS, and then they tell themselves and all their neighbors to terminate. And then when you do that, you take out a bunch of edges also. So we're going to show that when you do this, you take out at least half of the edges in each phase. in expectation. Okay. And if this is true, then you kind of expect that after about log n phases, the entire algorithm terminates, right? Log of the number of edges phases. So let's say m is the number of edges, okay? Then after log m phases, you expect the entire algorithm to terminate, right? Because each time you take out half the edges, so if you do this for log m times, then you're basically, you take out all of the edges, okay? And then when that happens, the algorithm, of course, terminates. Okay, so the main thing is to show that we take out about half the edges in expectation in each phase. And to do this, we're going to prove several claims. Okay, so before we do that, we need to define something. So let's say that you have, let's see, yeah, so I got a picture over here. Okay, so let's say that you have two nodes u and v. Okay, so so over here we've got u and we've got v. Okay, all right. So then we're going to say that u is going to preemptively remove v. Okay, u is going to preemptively remove v if, first of all, u is a neighbor of v. Okay, and then furthermore, u's value is less than u prime's value for all nodes u prime, which are either neighbors of u or neighbors of v. Okay, so for example, in this picture over here, right? So u's value is going to be 0.1. Okay. And then all of these other nodes have these other labeled values. And so in this case, you see that u's value is less than all of its neighbors' values. Okay. And in addition, u's value is less than all of v's neighbors' values. Right? Okay, so in that case, we're going to say that u preemptively removes the node v. Okay. And then also, so that's for the node u removing another node v, but we're also going to define a term where u preemptively removes an edge. Okay, so u is going to so if u preemptively removes the node v, then we also say that u is going to preemptively remove all of the edges of v. Okay, and the idea is that, because u here is the minimum value among all of its neighbors, then u is going to go into the MIS, right? And remember that when u goes into the MIS, u is going to tell all of its neighbors to terminate. And when u's neighbors terminate, then these guys are going to take out all of their adjacent edges. Okay, so u is going to tell v to terminate, right? And when v terminates, v is going to take out all of its edges. So that's why we say that u preemptively removes all of v's edges. Okay, so that's the definition of preemptively removes, and we're going to write it this way. Okay, we're going to say that if u preemptively removes v, we're going to write u double less than v. Okay, we're just going to use that notation. Okay, so now we're going to prove several claims. The first claim is that for any v, okay, there's only one u. There's at most one u which can preemptively remove v. Okay, there could be like 0 u's that preemptively remove v, but at most there's one u that does this. Okay, and the reason is simply that if u actually preemptively removes v, then u is a neighbor of v which has the minimum value, right? Because that's the definition of preemptively removes, right? If u removes v, then u has to have the minimum value among all of v's neighbors. Okay, and there can be at most one, there's only one node with the minimum value among these neighbors. So there can be at most one u which preemptively removes v. Okay, so that so that's the first claim. Okay, the second claim is that so let's define P to be the set of all the preemptively removed edges in each. So let's fix a phase first of all. Okay, let's just take. We're going to analyze things phase by phase. So let's just fix a phase. And then within that phase, we're going to let P be the set of all preemptively removed edges in that phase. And then we're going to let R be the set of all the removed edges in that phase. Okay, because you could have some edges which are removed, but not preemptively removed. Okay, so the claim is that all of these. The claim is that P is a subset of R. Okay, in other words, any edge which is preemptively removed is truly removed within that phase. Is actually removed in that phase. Okay, right. Okay, so to prove this, let's just take any edge which is preemptively removed. Okay, let's take some edge VW which got preemptively removed. Okay. Then then V has a neighbor U where U's value is less than all of V's neighbors' values and less than all of U's neighbors' values, right? Okay, so and because U's value is less than all of U's neighbors' values, then U is going to enter the MIS. Okay, so U will get removed in this phase. Okay. And then when U gets removed, then V is also removed. Okay, and then all of the edges which are incident to V are including this VW edge itself. Okay, they get removed in this round. Okay, so therefore this edge E, right, this preemptively removed edge is actually removed within this round. Okay, so that's claim 2. Okay, all right. So next, before we do the other claims, we're going to define this little notation here. We're going to define an indicator variable x of U, U preemptively remove V. Okay, so this is going to be 1 if U preemptively removes V, and 0 otherwise. Okay. All right. Now, whenever you have this XUV equal to 1, right, then U is going to take out V. Then, because we said over here that all the preemptively removed edges are actually removed, okay, then whenever XUV equals 1, then all of the edges incident to V are removed in that phase. Okay, and so let's let D of V be the number of be the degree of V, right? So that's the number of neighbors of V. Okay. So this means that if XUV equals 1 here, right, then all of these neighbors are removed. And so that means that D of V edges get removed. Okay, so next we're going to have another claim. So this claim is going to, it's basically going to look at how many edges get removed. Okay, so we're going to look at the sum over here. So this is a double sum. Okay, it's summing over all of the nodes in the graph. And then for each node, it's looking at all of the neighbors of that node. Okay, and then it's looking at whether this node U preemptively removes this neighbor. And if U preemptively removes V, right, then we multiply this by D of V. Okay, because we said that whenever U preemptively removes V, it's actually going to take out a number of edges. It's going to take out D of V edges. Okay, all right, so then we're going to look at this sum, and then we're going to show that this sum is actually not too large. It's at most 2 times the number of preemptively removed edges, 2 times P. Okay, where P is a number, P is a set of preemptively removed edges. Okay, so so the reason this is true is because if you take let's say an edge VW. Okay, so let's take an edge VW over here. Okay, then then this sum up here is going to count. It's going to count this edge. So this is going to be edge E over here. It's going to count this edge each time this edge is removed by any neighbor of V. Okay, so maybe V has, let's say a neighbor over here, right, and then maybe another neighbor over here, right, and then W could also have neighbors. Okay, so let's say W has this neighbor. Let's call him U double prime, and then maybe another U double prime here. U triple prime, let's say. Okay, so E here can potentially be removed by any of these U nodes, right? Either U or U prime or U double prime, U triple prime. Okay, any of these nodes can potentially remove V. Right. However, are these U nodes actually going to all remove V? So, for example, if you have all 4 U nodes over here, if they actually all remove this edge E over here, okay, then E, when you count the number of times that E gets removed, it would be counted 4 times, okay, because there are 4 of these U's that all remove E. But actually, it turns out that you cannot have so many U's which all remove E, okay, because what we said is that U is going to preemptively remove E if and only if either U is double less than V, or U is double less than W, right? And what we have by claim 1 is that there is at most one u, which is double less than v. Right? So here in this drawing, I'm drawing two different u's. And it cannot be the case that both u and u prime are both double less than v. Okay? And so that means that from this side v, there can be at most one node which removes this edge e. Okay. And also but it's also possible to remove e going from the w side. Okay. But on the w side, again, you cannot have two different u's which preemptively remove e. Okay. You can have at most one other node u double prime, which is going to be you can have at most one other. Can't I write over here? U double prime, which is double less than w. Okay. In that case, u double prime can preemptively remove e. Okay. And then here you have u is double less than v. Okay. Yeah. So both u and u double prime can preemptively remove e, but these are the only nodes which can preemptively remove e. So that means that e is preemptively removed by at most two other nodes. Okay, and so that means that if you look at the sum, then any edge which is preemptively removed is going to get counted at most twice in the sum. One from the v direction and one from the w direction. Okay, and because P here is a set of all preemptively removed edges, right? Then if you look at the sum, it's only going to count each preemptively removed edge twice at most. And so therefore, this entire sum is going to be no more than 2 times P. Okay, so any questions about this? Okay, so as a corollary to this claim, we have that if you look at the sum again, right, then this is also going to be less than or equal to 2 times r, where r is a set of all removed edges. Okay, and this is simply because P, right, the preemptively removed edges are a subset of r. Okay, so therefore, if the sum is less than 2p, it's less than 2r. Okay, so then we have one more claim. Okay, so this final claim is, so again, we're going to look at the sum over here. Okay, this is the same sum as on the previous page, but now we're going to look at the expectation of the sum. Because the sum is actually a random variable, right? Because all of these nodes are picking random values, so this xuv here is a random variable. So we're going to look at the expectation of the sum. Okay, and previously on the previous page, we were saying that this sum is not too large, right? It's no more than 2p. But now we're going to say that the expectation is not too small. Okay, it's going to be at least the number of edges. Okay, so h here is going to be the number of edges. Okay, so I'm not using e here because I'm using e for expectation. Okay, so h is the set of all the edges in the graph, and the claim is that the expectation of the sum is going to be at least the number of edges. Okay, so the reason for this is that if you look at, so we're going to use linearity of expectations. Okay, so then we're going to try to move the expectation inside, and we're going to look at each of these individual terms. Okay, now if you look at this individual term over here, right, then by definition, this is simply the probability that u, for each of these, it's a probability u preemptively removes v times the degree of v. Okay. And then, all right, so then u is only going to preemptively remove v if u's value is less than v's neighbors' values and u's neighbors' values, right? This is the only case where this happens. Okay. And now, how many such neighbors are there? Right? So if you look at all the neighbors of u and all the neighbors of v, right, then there are at most this number of neighbors. Right? D of u is the degree of u, and d of v is the degree of v. Right. However, the edge between u and v. Okay. So when you look at when you look at this thing, right, you're gonna count the edge between u and v twice. Okay. So so therefore, if you look at the total number of neighbors of u or v, right, that's going to be at most the degree of u plus the degree of v. Okay, and then each node is going to pick a random value r, right? So therefore, the probability that erase some of this stuff. Okay, so the probability that this happens, right, that u's value is less than all of these nodes' values, okay, is going to be, well, since there are at most this number of nodes, then the probability you have the minimum value among this number of nodes is simply 1 divided by the number of nodes, right? Like if you have like 10 nodes, then the probability that your random number is the smallest among these 10 random values is going to be 1/10. Okay, so then here we have that the number of neighbors is at most du plus dv. So the probability that u has the minimum value among all of these neighbors over here is going to be at least 1 divided by du plus dv. Okay, so then, so therefore the probability that u preemptively removes v, right, is going to be at least this thing, okay, 1 over du plus dv. Okay, and so the expectation of this xuv indicator times dv is simply dv times times the previous value times the probability that u double SMV. Okay, so then now let's look at this sum that we're trying to figure out, right? Because we're trying to figure out this expectation of this entire sum. Okay, so we're going to break the sum into 2 parts. Okay, so notice that so this sum is going to iterate over all the nodes, and then for each node, it's going to iterate over all the neighbors of that node. And so that means that for each edge in the graph, okay, that edge is going to get counted twice, right? It's going to get counted once from the u direction and then once from the v direction. Okay, so therefore you can take this sum over here and you can expand it into these 2 things, right? So here we're counting u preemptively removes v, and then here you're counting v preemptively removes u. Okay. Right, and then by the by what we have over here, we have that. Let me clear this up a little bit. We have that this thing, right, is going to be at most equal to this value. Okay, dv divided by du plus dv. Okay, and then over here, if you use the same argument, you have that this thing is going to be at it's going to be at least du divided by du plus dv. Okay, yeah. So therefore, once you add these 2 together, right, they're going to cancel out, and you get that, and you can simplify the entire sum to simply you're just adding up over all of the edges. Okay, so therefore the entire sum is going to add up, the expectation of this entire sum is going to add up to the number of edges. Okay, so any questions about this part? Okay, so once we have these 4 claims, then we can prove the lemma that we were trying to prove, which is that in each phase, we're going to take out half the edges in expectation. Okay. Because what we showed is that, so now we're going to combine all of these claims, and we have that this sum over here, right, in expectation, it's going to be at least the number of edges. Okay. But also by the previous claim, you have that this sum here is less than 2 times the number of preemptively removed edges. Okay. And so that means that when you combine these 2 things, you get that the 2 times the expected number of preemptively removed edges. Okay, is going to be so h is going to be less than or equal to 2 times the number of preemptively removed edges. Okay, and so that means that in expectation the and then this this is going to be 2 times less than or equal to 2 times the expected number of removed edges, right? Because P is a subset of R. And so this means that in expectation, in each phase, the expected number of edges that you remove is going to be at least half of the total number of edges. Okay, and this is what we wanted to prove. Okay, every phase you take out half the edges in expectation. Okay, so so we're almost done. Okay, so once you have this lemma, then it's pretty easy to show that this algorithm is going to terminate in logarithmic number of rounds, not only in expectation, but also with high probability. Okay, yeah, so, okay, so let's do that. Okay, so we're going to show this the entire algorithm terminates in logarithmic number of rounds with high probability. So to do that, we need one more corollary, which is that, with probability at least 1/3, we take out at least 1/4 of the edges in every phase. Okay, so so the lemma says that in each phase, you take out half the edges in expectation. Okay, but it doesn't tell you what the probability of taking out half the edges is. And now we're saying that with probability at least 1/3, you take out 1/4 of the edges in each phase. Okay, and this is true because the probability less than, oh, okay, right. Because otherwise, if the corollary is false, then the probability that you take out less than 1/4 of the edges, okay, that's going to be more than 2/3. Right. Okay, so yeah, because the opposite of this statement is simply that you take out less than 1/4 of the edges with probability at least 2/3. Okay. But then the number of edges that you take out in each round in expectation, okay, you have a greater than 2/3 probability of taking out less than 1/4 of the edges, right? And plus, you have a less than 1/3 probability of taking out more than 1/4 edges, or more than 1/4 of the edges. Okay. But at most, in the second case, where you take out more than 1/4 of the edges, at most you can take out all the edges, right? And so that means that in expectation, you can take out at most this expression. Okay, you can take out at most this number of edges in expectation in each round. And this is actually less than half of the edges. Okay, right, and that's a contradiction, right? Because the lemma says that we take out half of the edges in expectation. Okay. Oh, I'm sorry. I should not write E here. I should write H, okay, because I was using H for the set of edges. Okay. All right. Yeah. So therefore, with at least 1/3 probability, you take out at least 1/4 of the edges in every phase. Okay. So then once you have this, then we can finish up the analysis of the algorithm. Okay. So we have a theorem which says that this algorithm is going to compute a maximal independent set in at most 42 times log n number of rounds with high probability. Okay, so you'll see why I chose this number 42 here. Okay, but it's basically order of logarithmic rounds. We're gonna compute an MIS. Okay, so let's do this analysis. We said that with at least 1/3 probability, you take out at least 1/4 of the edges in a phase. Okay, so we're going to say that a particular phase is good if this actually happens, if we actually take out 1/4 of the edges. Okay, so therefore the probability that a phase is good is at least 1/3. Okay, and also all of the phases are independent from each other, right? Because each time you run this algorithm, you just or each phase you pick a completely new random number. Okay, so all the phases, none of the phases affect each other, so they're all independent. Okay, so therefore, what you expect is since each phase has a 1/3 probability of being good, then if you run for 42 log n phases, okay, you expect 1/3 of those to be good. Okay, so you expect at least 14 log n good phases. Okay, we're going to set this to be mu here. This is our expectation. Okay, and now the question is, you expect to get 14 log n good phases. So what is the probability you get less than half your expectation? Right? What's the chance you get less than 7 good phases in 42 rounds, 42 log n rounds? Okay, so now we can use the Chernoff bound to bound this. Okay, because remember the Chernoff bound, when you have an expectation, and the expectation is a sum of independent random variables, right? Then we expect that when you actually run this process, you get something close to your expectation. And you have very small, exponentially small probability of deviating substantially from your expectation. Okay. So here we're asking, what's the chance you get less than half of your expectation? Okay. So now, if you plug in all these values into the Chernoff bounds, so I forget which version of the Chernoff bounds this is, but it's one of those versions, right? So if you plug in all of these values, you're going to get that this is going to be less than 1/n. And in fact, this is why I chose all of these numbers, like the 42 and stuff. Okay, that was all to make the final constant in this expression work out to less than 1/n. Okay, if you choose a different value, if you choose like 52 or something, you're going to get it's basically going to you're going to have some sort of constant factor, or sorry, you're going to have some constant in the exponent, and whatever value you choose over here, the larger this value, the larger this exponent c is going to be. Okay, but in our case, we just want to have at least a, or at most a 1/n probability, and so that's why I chose 42. Okay, there's nothing special about 42. Okay, all right, so then what we see is that with a high probability, with at least 1 minus 1/n probability, okay, you're going to get at least 7 log n good phases. Okay. Now, each time you get a good phase, you're going to take out at least 1/4 of your edges, right? Because that's what it means to be a good phase. Okay. So therefore, if you get 7 log n good phases, right, then the number of edges that remain after this is going to be at most 3/4 to the 7 log n power. Okay. And then if you plug in all these numbers over here, you're going to get that this is going to be less than 1/n squared. Okay. Right. Okay. And so this means that the number of edges which remain after 7 log n phases is going to be less than 1/n squared fraction of the initial number of edges. Okay. Now, initially, you have at most order n squared edges. Okay, so if after all of these good phases, you have at most a 1/n squared fraction of these edges remaining, then that means that you only have 1 edge left after 7 log n good phases. Okay, and then after that, if you run for one more phase, then you're going to take out that single remaining edge, and then the algorithm terminates. Okay, so in summary, if you run for 42 log n phases, right, then you expect to get at least 7 log n good phases with high probability. And if you get 7 log n good phases, then that allows you to remove all of the initial edges. And then the algorithm terminates. Okay, so therefore the algorithm terminates after 42 log n phases with high probability. Okay, any questions about this? Okay, so all right. So then, in that case, we're gonna look at one more graph algorithm. Okay. Oops. Sorry. What? All right. So how do I maximize this? Okay. Oh, sorry. 1 second. I need to open up a pen here. Let's see. I want to draw the red. Okay. All right. This is very slow. Why is this happening? Sorry, 1 second. Okay, so let me just make this a bit faster. What's making things slow? What is this? Oh, all right. Well, I guess all right, I can kill this one. Okay, the antivirus thing. Let me stop this. Oh, okay, all right, fine. All right, sorry. Okay, so let's see. Where's my? Okay. Sorry, 1 second. 1 second. All right. All right. I'm sorry, guys. Just let me close this thing up over here. All right. Okay. So this is okay. Anyways, there's a lot of lag on my computer, but let's see if this still works. Why is this so slow? All right. See, I can't even scroll over here. This is ridiculous. All right. Okay, this is really, okay, so we're gonna look at one more algorithm over here, one more graph algorithm. Okay, so this graph algorithm is going to be called global min cut. All right, so let's first define the problem. Okay, so we're given a connected undirected graph. Wow, this is very slow. I can't even draw on here, so this is really annoying. Okay, all right, so we're given a connected undirected graph. Okay, and what we want to do is to find a cut of minimum cardinality. Okay, so you're given a graph, let's say like this, right? And then you just want to cut this graph, and then the size of the cut is simply the number of edges which cross between the cuts. Okay, so you have an A side and a B side, so you want to minimize the number of edges which cross this cut. Because we have an undirected graph, so we don't care which direction the edges do not have any directions. Okay, so we're simply looking at how many edges cross this cut, and you want to minimize that. This is called the global min-cut problem. Now, this is very similar to another problem we looked at, which is minimum ST cut. Okay, so remember for the minimum ST cut, what happens is that you start with two nodes, S and then T. Okay, and now you have to find a cut where S is in one side of the cut and T is in the other side of the cut. And then you try to minimize the number of edges which cross from the S side to the T side. Okay, all right. So there are two differences between global min cut and ST cut. So one difference is that in ST cut, the edges have directions. Okay, so for example, some of these edges might be going from S to T, in which case from A to B, in which case you count them in the ST cut. Okay, but then you could have other edges which go from the B side to the A side, and you do not count them. Okay, so whereas in global min cut, we're dealing with an undirected graph, so you simply count all of the edges which go between A and B. So that's one difference. Okay. The other difference is that in ST cut, you have a special node S and a special node T. Okay, and you want to make sure that your cut separates S and T. So S is on the A side, and T has to be in the B side. Okay. But for the global min cut, you don't have these special nodes, so you can go for any cut you want. Okay. All right, so this global min cut actually has a bunch of applications, but I don't really know what these applications are. Okay, but apparently it has lots of applications. Okay, all right, but we're going to try to solve this problem, and one way that you can solve it is to just use a ST cut algorithm to try to solve global min cut, right? Because we looked at a bunch of algorithms to solve ST cut. And then we can try to apply those algorithms to solve the global min cut. Okay. So for example, one thing that you can do is if you're given a graph, right, and if you want to find the global min cut, then you can just pick any node to be your S node. Okay. And then from this S node, you can try to separate this S node from all possible T nodes. Okay, so you can pick a node T1 here, and then you can try to find the minimum S to T1 cut. Okay, and then you can try a different node, let's say T2, right? So you can try, let's say T2 over here, right? And then you can find a different cut. Okay, so so let me just keep all these things on there. Okay, and then you can find a T3, and then you can try to find a minimum S to T3 cut. Okay, so then you have so in total you're gonna have you're gonna produce n of these cuts, or n minus one of these cuts. Okay, from S to every other node. And then you're just going to take the minimum cut among all of these as your global minimum cut, right? Because your global minimum cut has to separate this this node S from some other node. Okay, right? So if you look at the minimum among all of these n minus one minimum S to T cuts, then that is equal to the global min cut. Right. However, if you do this, then you're going to have to run the ST cut algorithm order n times. Okay. And so this would make it seem like the global min cut problem actually takes longer to compute than the minimum ST cut problem. But this is actually not true, because what we're going to see is that you can actually compute the global min cut more efficiently than you can compute a minimum ST cut. Okay, we're going to give a randomized algorithm for global min cut, which is faster than computing the min cut between some particular pair of nodes, S and T. Okay, so this algorithm is by David Karger, So it's based on this operation called contraction. Okay, so let's first look at what this contraction operation is. Okay, so suppose you have a graph over here. Okay, and now let's pick an edge to contract. So let's suppose you take this edge E over here between U and V, and you want to contract this edge. Now the first thing is that we allow multiple edges between a pair of nodes. Okay, so here we have like 2 edges between U and V. Okay, but we're going to try to contract this E edge. And to contract simply means that you're going to take the one of the endpoints, let's say U, okay, and you're going to move it over to V. Okay, so just imagine taking U and then dragging it over to V. And then all of the edges, so as you drag U over to V, all of the edges from U are going to follow. Okay, so A is going to also end up over here, right? So A is going to end up, so if you drag U over to V, then A is going to end up over here, and then this F is also going to end up over here. Okay, and then after you move U over to V, then U and V are going to become one big node. They're going to become this super node here, W. Okay, so that's the contraction operation, right? You just take out the edge between U and V, and then you take all of the edges from U to its neighbors, and then move them over to the new super node. Okay, so that's the contraction operation. Does that make sense? Any questions about that? Okay, so once we have this contraction operation, then we're going to use it to compute a global min cut. Okay. And the algorithm is actually very simple. So what you do is, if you have a graph, you're going to pick a random edge, okay, and then you're just going to contract that edge, okay, and then once you contract that edge, then you're going to have fewer edges, okay, and also fewer nodes. You're going to have one less node and possibly many fewer edges. Right? Because each time you contract, you take 2 nodes and you combine them into 1 node. Okay? And then you're just gonna, and then after that, you're gonna get a new graph, right? So for example, if you contract over here, you're gonna get a new graph. And then in this new graph, again, you pick a random edge and then you contract it. Okay? And then after you do that, you're gonna have 1 fewer node. And so you just keep repeating this process until eventually you only have 2 nodes. Okay, let's say U1, V1. And then these 2 nodes are going to have lots of edges between them. Okay? And then you're just going to take all of those edges between U1 and V1, and you're going to say that this is your minimum cut. Okay? So remember that we allow multiple edges between 2 nodes, right? So for example here, right, in this original graph, you have 2 nodes between U and V, and in this new graph, you have like you have 2 edges between U and V, and then in this new graph, you have like 2 edges between, these 2 nodes. Okay, so that's the entire algorithm. Pick a random edge, contract the edge, and then keep doing this until you're down to 2 nodes. And then just take all the edges between those 2 nodes, and that's your min cut. Okay. All right, so yeah, so let's first of all look at an example of this algorithm. Okay, so suppose you start with this graph. Okay? Now in this graph, the min cut is actually so you have these white nodes and you have the red nodes, and the min cut is actually the edges going between these 2 sides. Okay, so it's the min cut has size 3. Okay? Right. So let's run this contraction algorithm. So suppose that the first time you pick a random edge, you happen to pick this edge over here. Okay. All right, then when you contract it, you're gonna get this situation over here, right? You're gonna bring these 2 nodes together, and then you're gonna drag all the edges along with this process. Okay, all right. Okay, so then next, you're gonna pick another random edge, and let's say that you pick this edge over here. Okay, you're gonna contract this edge, and that's gonna move some of these edges around. Okay, and then you're gonna keep running. Let's say that you pick this edge next. You're gonna contract it. Right? And then you just keep doing this over and over. Okay. So you see that each time you do this, right? So this is the first time you have like, you start with 10 nodes and then you end up with 9 nodes, right? So each time you do this, you're going to have 1 fewer node. Okay. And then eventually, this is what you're going to end up with. Okay. So suppose that in your execution, eventually you happen to end up with this thing. Okay. And then in this case, you're just going to take these 3 edges between the white and the red node, and you're going to say that this is your min cut. And in this example, this is this is actually correct. right? These 3 edges are actually the min cut. But of course, this algorithm is not going to always produce the min cut. Okay, so this is a randomized algorithm, and actually it can make mistakes sometimes. Okay, so this is a Monte Carlo algorithm. Okay, so one example where it can make a mistake is so suppose in the first step, instead of contracting this edge, okay, suppose it instead contracted suppose it contracted this edge. Okay? So this edge is actually in the min cut. But if you happen to randomly pick this edge and you try to contract that edge, okay, then if you run the algorithm, then after you contract the edge, you lost one of your min-cut edges. Okay, and this is going to cause the entire algorithm to not work correctly. Okay. So you notice that in this correct example over here, right, we never contracted any of these min-cut edges. Right, we only contracted these other edges which were not part of the min-cut. And so therefore, after all of the contractions, you still have your min-cut edges in the graph. And that's why in the final step, all the remaining edges are exactly equal to the min-cut. But if your algorithm happened to pick one of these min-cut edges, let's say like this one, right, and it contracted that edge, then after you finish the algorithm, you would have lost your min-cut, and your output would not be equal to your min-cut. Okay. Yeah. So therefore, you see that there's some probability that this algorithm works correctly. It's not always going to work correctly. Okay. Right. So now let's analyze the probability that this algorithm works correctly. Okay. Yeah. So the claim is that this contraction algorithm is going to return a min-cut with at least 2 over n squared probability, where n is the number of nodes. Okay. So this is actually not a very high probability. Right? Because if you have like 1,000 nodes, right, then you only have like a 2 in 1 million probability of returning a min-cut. Okay. But we're going to see that this is at least a positive probability, right? So at least there's some chance that this algorithm works correctly. And we're going to see that even though this probability is not too large, in the end, if you do this the right way, you can still use this to produce an efficient min-cut algorithm. Okay. But let's first of all prove that if you run this contraction algorithm once, then you have at least a 2 over n squared probability of getting a min-cut. Okay, so to do this, let's look at the graph. So say that this is your graph, okay, and let's let f star here be the actual min-cut. Okay, so we don't know what this f star is initially, but there's some sort of min-cut, and so let's just focus on this min-cut. And let's say that k is the number of edges in this min-cut. Okay, so in the end, you want to return a cut with size equal to k, not larger than k. Right. So we said that the contraction algorithm is going to work correctly if we never contract one of these min-cut edges. Okay, so there is some sort of min-cut, and if when you run this contraction algorithm, you never try to contract any of these min-cut edges, then in the end, you're still going to have these min-cut edges being preserved in the graph. Okay, then in the end, all of A star is going to shrink down to one big node, and all of B star is going to shrink down to one big node, and then you're just going to have these edges in F star between the A supernode and the B supernode. Okay, if you never contract any of these F edges. So then the question is, what is the probability that we do not contract one of these F edges, one of these min-cut edges? Okay. Well, the probability is simply that if you have E edges in the graph, okay, then since F has size k, then the probability you do contract one of these F edges is going to be k divided by the number of edges. Okay, so this is bad, right? We don't want to contract one of these edges. Okay, and this happens with k divided by E probability. Okay. Right. So now the question is, what is E? Okay, or E is the number of edges. Okay, but how large is E? Okay, because we want to bound this overall probability. Okay. Now, the key observation is that because your min-cut has size k, okay, then every node has to have degree at least k. And this is because, if you have a node with degree less than k, okay, so say this node has degree k minus 1, okay, then the min-cut is simply that, you can just cut this node off, right? And that would only cut k minus 1 edges. Okay, so that would already be a min-cut of size k minus 1, which is smaller than your min-cut of size k. Okay, so that's a contradiction. So therefore, you cannot have any nodes with degree less than k. Okay, so every node has degree at least k. And so that means that the number of edges is going to be at least 1/2 times k times n. Okay, because you have n nodes, right? Each node has degree at least k, right? And if you add up all of these degrees, you're going to count the number of edges twice, right? You overcount by a factor of 2. So therefore, the number of edges is going to be at least 1/2 times kn. Okay, and that means that k divided by the number of edges, okay, is going to be at most is going to be less than or equal to 2n. Okay, sorry about this. Okay, so that means that k divided by the number of edges is going to be at most 2 divided by n. Okay, and so that means that in this first step, okay, so we're just looking at the very first step, okay, where you have e edges and you have a cut of size k. Then in the first step, the algorithm contracts a min-cut edge with probability at most 2 divided by n. Okay, so that means that in the beginning, the algorithm has a very good chance of not hitting one of these special edges. Right? We don't want it to contract these f edges. Okay, and in the very first step, because your min-cut is small, right? That's why it's the minimum cut. It's small. Okay, it's small compared to the number of edges. So therefore, you have a very small probability of actually contracting one of your min-cut edges. Okay, so that's a good thing. Okay, but that's only for the first step, right? So what about these other steps? Okay, so now let's look at the probability of contracting a min-cut edge as you go on, as you progress with the algorithm. Okay, so the problem is that as you go on with this algorithm, then you have fewer and fewer edges in your graph. Right? Because you keep contracting things and that removes edges. So you have fewer and fewer edges. Okay. And since you're trying to make sure you don't contract one of these special edges, one of these f edges, then but if you have just very few edges, then there's actually a pretty good chance you will contract one of these special f edges. Okay. So in other words, as the algorithm progresses, you have a higher and higher probability of actually contracting one of these special f edges. Okay, so you have a higher and higher probability of the algorithm failing. Okay, all right, so let's look at what this probability is as you keep running this algorithm. So here, let's let g prime be the graph that you get after j iterations. Right, so after you've contracted j nodes, then suppose you're left with a graph g prime. Okay, then in this graph, since each iteration you take out one node, right? And then you form a supernode with it. Then in G prime, you have n minus j supernodes. Okay, because each iteration you take out one node. Okay, so then in G prime you have n minus j supernodes. And suppose up to now, right, after you've run j iterations, okay, we're still in a good situation where we still have not contracted any of these f star edges. Okay, so suppose our algorithm is still in a good state. Okay, then the min-cut is still going to be k, right? Because you haven't contracted any of these k special edges. Okay, and then because the min-cut is still k, then by the same argument as before, the number of edges which are remaining in G prime. Okay, so E prime is the number of edges in G prime. This has to be at least 1/2 of k times the number of nodes in G prime. Okay, because again, all of these supernodes in G prime, they have to have degree at least k, right? Otherwise, your min-cut is going to be less than size k. Okay. So therefore, your number of edges in G prime is going to be at least 1/2 of k times m prime. Okay. And now your probability, and now in the jth iteration, what's the probability that you contract one of these min-cut edges, right? What's the probability this bad thing happens? Well, it's going to be equal to k. Because your min-cut has size k, then the probability is going to be k divided by the number of edges. Okay, and we said the number of edges is at least 1/2 k m prime. And so therefore, again, the probability that you remove one of these min-cut edges is going to be 2 divided by m prime. Okay, in the first round, it was 2 divided by n, and now it's 2 divided by m prime, and where m prime is equal to m minus j. Okay, so therefore you see that the probability we take out one of these min-cut edges is actually increasing. Right? So as you run more and more rounds, the m primes get smaller, and so therefore you have a higher probability of removing one of your special edges. Okay. All right. So therefore, in this iteration, the algorithm has a less than 2 over n prime probability of contracting a min-cut edge. Okay. All right. And so now let's let EJ be the event that we do not contract a min-cut edge. Okay. So EJ is a good thing, right? Because we don't want to contract a min-cut edge. Okay. So let's let EJ be this event. Okay. Right. Then our probability that in the end we actually get a min-cut. Okay, how do you actually get a min-cut in the end? Well, what has to happen is that in every iteration, you do not contract a min-cut edge. Right? So you need to have E1. Okay, you need to make sure that in the first iteration, you do not contract a min-cut edge. Okay, and you also need E2. In the second iteration, you don't contract a min-cut edge. Okay, and you need this for every iteration. And in total, you're going to run for m-2 iterations, right? Because every iteration you take out one node and you stop when you have 2 nodes. Okay. Yeah. So therefore, the probability that you actually get a min-cut in the end is going to be the probability that all of these events, E1, E2, all of them happen. Okay. All right. So to evaluate this probability, you just have so you have this thing over here, right? So it's equal to the probability that E1 happens. Times the probability that E2 happens, assuming E1 happens, right? Conditioned on E1, and then so on, right? So you just multiply together all these conditional probabilities, okay? All right, and what we said is that E1, right? So the probability that you don't contract an edge, a min-cut edge in the first iteration is going to be at least 1 minus 2 over n. Okay, it's going to be at least 1 minus 2 over n. Okay, so therefore you have that PR of E1 is going to be this, right? And then we have that the probability of E2, that in the second round you don't contract a min-cut edge. Okay, so that's going to be at least 1 minus 2 over n minus 1, right? Because in round 2, you have that m prime here is equal to m minus 1. Okay, so therefore the probability of E2 is going to be at least 1 minus 2 over n 2 over n minus 1. Okay. And so in general, the probability of EJ is going to be at least 1 minus 2 over n minus j. Okay, so you can write out the entire probability like this. Okay. All right, so now we're going to simplify this expression, right? So you can simplify this to this thing. And once you simplify, what you see is that a lot of these terms are going to cancel out. Okay. So, for example, the next term over here would be n minus 4 over n minus 2. Okay. Wow, this is so slow. Okay. And so the n minus 2 over here and the n minus 2 over here are going to cancel. Okay. And then, yeah, so if you just expand out this entire expression over here, you're going to see that a lot of terms cancel out. And in the end, the only things which don't cancel out is going to end up being something like this 2 over n squared thing over here. Okay, these are the only terms that remain after this. And so that means that the probability that you don't contract a min-cut edge in any iteration is going to be at least 2 over n squared. Okay, and if you never contract these min-cut edges, then in the end, this algorithm is going to return a min-cut. So therefore, the algorithm succeeds with probability at least 2 over n squared. Okay, any questions about this? Why if one node has less than k degrees than a star? Okay, yeah. So I guess you're asking about. Go back to the previous page. I guess you're asking about this fact over here, which is that every node has degree at least k. Is that what you're asking about? Yeah, okay. Yeah, so the reason is that suppose you have some node, let's call this guy V. Oops. Sorry. All right, suppose you have a node V over here, and this has degree less than k. Okay, suppose it's got degree k minus 1. Okay, then what you can do is, so you have a graph like this. So you have a node V over here with degree less than, with degree k minus 1. So you can just make a cut where you just cut V itself. Okay, so this here is going to be A, and this is going to be B, right? And the size of this cut is simply the number of edges coming out of V, which is k minus 1. Okay, so in that case, you have a cut of size k minus 1. Okay, but our assumption is that your min cut has size k. So if your min cut has size k, there cannot be a node with degree k minus 1. Because if there is such a node, your min cut would have size k minus 1. Okay. Yeah. Okay. Yeah. And then later on, it's the same argument. Okay. So later on, when you have as long as you can preserve your min cut and it's still size k, then you can show that the degrees of all the nodes which remain in this contracted graph, right? They all have to be at least k, because again, if it's less than k, then your min cut would also be less than k. Yeah. Okay. Yeah, and the reason this is important is because we need to make sure that there are lots of edges in the graph, because in that case, it's unlikely that when you pick a random edge, this edge is actually one of the min-cut edges. Right? If there are only a few edges in the graph, then when you pick a random edge, it's very likely, it's quite possible that you contract one of your min-cut edges, in which case your algorithm fails. But if there are many, many edges, then that's unlikely. However, the failure probability does go up as you keep running this algorithm for more and more iterations. Okay. Oops. Right. So. Okay. So now what we have is that if you run this algorithm once, then it succeeds with probability 2 over n squared. Okay. And this is a pretty low probability, right? So we actually want this algorithm to have a higher probability of success. Okay. So then in order to do that, you can simply run the algorithm many times. Okay, so the idea is that if you run it once and it's got let's say a 1% chance of succeeding, then if you run this thing 100 times, you've got a much higher chance of succeeding. Okay, right. So if you run this algorithm once, then it's basically got a 2 divided by n squared probability of succeeding. So we're not just going to run this once, we're going to run this many times. And in fact, we're going to run this n squared times log n times. Okay? And the claim is that if you run the previous algorithm n squared times log n times, then the probability that all of these executions fail is going to be quite low. It's going to be at most 1 over n squared. Okay? And the reason for this is simply that, each time you run this algorithm, you have a you have a 1 minus 2 over n squared probability of failing, right, of not finding the min cut, okay? But the probability that you fail but since you're going to run the algorithm for n squared log n times, the probability that you always fail, right, is going to be this expression over here, okay? And so now you can just simplify this thing, so you can pull the n squared sort of inside the exponent, right? So you get this expression over here, right? And then this thing inside is basically going to be like 1 over e, okay? Or it's going to be less than or equal to 1 over e. And so the whole thing is going to be, if you simplify it, the whole thing is going to be less than 1 over n squared probability. Okay. Yeah. So again, the idea is that each time you run this, you have a 2 over n squared probability of succeeding. So if you run this for n squared times, right, and then again by another factor of log n, so if you run for n squared log n times, then you're very likely to succeed. Yeah, so that's the algorithm. Okay, so we're all right. Actually, there's this little picture over here which shows how this new algorithm works. Okay, so we're just going to run this algorithm many times. Okay, and it could be that so here the min cut is size 3. Okay, so it could be that the first time you run this, you get this as your outcome, and this is actually a min cut of size 4. Okay, and that's because in one of these steps you actually cut one of these min cut edges. Okay, so you lost your min cut, so this trial failed. Okay, and so you run again, right? And then you again, you happen to cut one of your min cut edges, so in the end you didn't get the min cut. Okay, but if you run for many times, then it's quite likely that you have at least one trial where you do not cut any of these min cut edges, and then you do get your min cut. Okay, okay. So then how do you know which trial is actually successful? Well, you just look at the size of the cut you got after each trial, and then you just take the smallest one. Okay, so the first time you got a cut of size 4, next time you got a cut of size 4, and then what is this? This might be like 5 or something. Okay, yeah, so you kept getting all these different cuts, and just whichever one is the smallest, that's the one that you return in the end. And it's very likely that the smallest cut is actually the min cut. Yeah, so that's the algorithm. Okay, so I'll just say a few more things about this. So first of all, if you look at the time complexity of this algorithm as we presented it, okay, it's actually pretty slow because you need to run for a total of n squared log n iterations, right? And then each iteration, you need to go through this contraction process, and then this you can show can actually take order m time. Okay, so in total, this is going to take something like m times n squared log n time if you run this current algorithm. But it turns out that you can improve this algorithm. Okay, so when you improve this algorithm, you can basically remove this factor of m over here. Okay, you can make it much faster. You can make it run in basically n squared log cubed n time. Okay. So I'm not going to go through this entire algorithm, but basically the main idea for this algorithm is that what we said is that initially it's very likely that a round is successful, right? Meaning that you do not cut a min-cut edge in a round, right? Because initially there are many, many edges and there are just a few min-cut edges, so it's unlikely that you happen to pick one of these min-cut edges to contract. Okay. Yeah, so in the beginning of the algorithm, you're very likely to succeed. However, as you keep running the algorithm, then there are fewer and fewer nodes left and fewer edges. And so then your failure probability increases. Okay, so the longer you run this algorithm, the more likely you are to fail. So the idea for this improved algorithm is that let's not run the algorithm till the very end, till we're left with only 2 nodes. Because by that time, we have a very high probability of failing. Okay. So instead, let's only run the algorithm until we have n divided by root 2 nodes, which remain. Okay, and you can show that when you only run the algorithm for that number of steps, then your failure probability is actually pretty high. Your success probability is actually pretty high. Okay, you have at least a 50% chance that you have not. You have at least a 50% success probability. Okay, so basically it's something like, if you look at this analysis, okay, so if you don't go till the very end, okay, if you only go till something like, n divided by root 2 over here, okay, then if you look at this term over here, sorry, this expression, right, you're not going to have all of these terms in the end, and then when you compute this whole thing, you're going to see that if you stop at this point, you're going to have at least a 1/2 success probability. Okay. All right, but the problem is that you still have this big. So if you stop at this point, you still have a lot of these nodes remaining, and you still don't know what your min-cut actually is. Okay. All right. So then what they do is they first run until you only have this number of nodes left, right? And then whatever graph you get at this point, okay, let's call that graph G prime. Okay. Then they're going to run the contraction algorithm starting from G prime. They're going to run the contraction algorithm twice. Okay, starting from the same graph, they're going to run it twice. And then they're going to return the best of these 2 cuts. Okay, so maybe the first time you run it, you get a cut of size 10, and the second time you run it, you get a cut of size 8. Okay, then you're going to take the size 8 cut. Okay. And by some sort of analysis, you can show that when you do this, okay, when you stop at G prime, and then you run from G prime twice, and you take the better of these 2 things, then you actually get a much higher probability of finding the min-cut. Okay, so this is kind of related to this thing called the power of 2 choices. Okay, so there's this type of algorithm where you basically you do things twice and then you take the better outcome. Okay, so that's called the power of 2 choices. And it turns out that just by doing this, by doing things twice and then taking the better one, you can oftentimes get a much better result than if you just do it once and then you take whatever you get. Okay, yeah. So anyways, so there's this way to improve the algorithm so that it has this better running time, and then actually Karger improved it again so that in the end it has something like basically order m running time. Okay, m times log cubed n. Okay. And this running time is much better than so this is to find the global min-cut, right? And this is much better than trying to find a global min-cut using max flow, okay? Because max flow algorithms, they basically, at least the traditional algorithms have complexity something like m times n, okay? And this Karger algorithm only has complexity basically order m. Yeah. So there are some newer max flow algorithms which have something close to order n complexity. Okay, but those are very recent, and so yeah, so for a long time, this randomized algorithm for global min cut was much better than the best deterministic algorithm. Okay, right, and then one final thing I'll say is that this algorithm can actually handle, so currently we're just talking about unweighted graphs, okay, but you can actually generalize this in a very natural way to handle weighted graphs, positive weights. Okay, any questions about this? Okay, all right, so then, oh, what happened? Sorry, one second. All right, okay, so then that's all we're gonna talk about for the randomized graph algorithms. So we're gonna look at one, where is this? Yeah, so we're gonna look at one more algorithm, which is, okay. Yeah, so we're gonna look at one more randomized algorithm, okay? And then after that, we're going to move on to a new topic. Okay, and this new algorithm is about a randomized algorithm for linear programming. Okay, yeah. So I guess I have like something like 4 minutes left. So I'm probably not going to get too much through this. But let me just sort of introduce the problem to you first of all. Okay. So yeah. So we're going to see how to use randomized algorithms to solve linear programming. And so linear programming is actually it's a very, very important type of algorithm in computer science. Okay, so yeah, so there was a list of like the 10 most important algorithms of all time, and linear programming is like way up there. Okay, so the other algorithms are like sorting and FFT and stuff like that. Right. So linear programming is also like a hugely important algorithm. And basically, linear programming can model a situation where you have some sort of objective function that you try to optimize. Okay, so you have a function that you want to make it as large as possible or as small as possible. Okay, and then, but in order to achieve this objective, you're subject to a bunch of constraints. Okay? But these constraints are also linear constraints. Okay, so you're trying to maximize a linear objective function subject to linear constraints. And then you allow, and the values that you allow to satisfy this function, you allow any real values. Okay, yeah. So that's basically what the linear programming problem is. Okay, and it turns out that you can use linear programming to model many types of other problems. Okay, and so once you have a efficient linear programming algorithm, you automatically have efficient algorithms for a big class of other problems. Okay, so that's why linear programming is so important. All right, now let me just try to introduce or at least motivate the linear programming problem. Okay, all right. So let's consider this situation. So suppose you have a farmer. Okay, and the farmer has 100 acres of land. Okay, and so and on this land he can plant things, and he's trying to make a lot of money by planting things. So this farmer can either plant wheat or barley or both wheat and barley. Okay. However, when he plants things, he's subject to some constraints. Okay, so for example, this farmer only has, let's say, 420 kilograms of fertilizer. Okay, and he's got 160 grams of pesticide. So if you want to plant things, you need to have both fertilizer and pesticide. And let's say that this farmer has just 420 kilograms of fertilizer and 160 of pesticide. Okay, and also for each acre of barley that this guy plants, okay, he needs 5 kilograms of fertilizer and 1 kilogram of pesticide. And also for each acre of wheat, he needs 3 kilograms of fertilizer and 2 kilograms of pesticide. Okay. And now suppose that wheat sells for $3 per acre. Okay, so for each acre of wheat that he plants, he can make $3. And for barley, he can make $4 per acre. Okay. And so yeah, so these are just example figures, right? So in practice, you can make a lot more money than that. Okay, but I'm just using simple numbers here. So then the question that we want to answer is that how many acres of wheat and barley should the farmer plant in order to maximize his income? Okay. And so the way to solve that problem is that we can let W and B represent the amount of wheat and barley that the farmer plants. And so what the farmer is trying to maximize is that for each acre of wheat, he makes $3. right? And for each acre of barley, he makes $4. So he's trying to maximize this linear objective, 3W plus 4B, right? But when he does that, he has to satisfy all of these constraints over here, right? Because for each acre of wheat and barley, he needs to use a certain amount of fertilizer and pesticide, and he only has a limited amount of fertilizer and pesticide, right? And furthermore, he only has 100 acres of land, right? So at most, he can plant 100 acres of wheat or 100 acres of barley or some combination. Okay? So he's got a bunch of these constraints that he needs to satisfy. Okay, and all of these constraints turn out to be like you can express them using linear functions. Okay, so I'll just show you this this thing, and then we're going to go through it more carefully next time. Okay, so you can phrase the entire problem as sort of these this linear objective function subject to these linear constraints. Okay, so then next time we're going to look at how to sort of think about this in a very nice way. And then we're going to develop a randomized algorithm based on this interpretation of these constraints. Okay, yeah. So so we're out of time for this lecture. So I'll talk about this next week. Okay. Any questions about anything? Okay, and as I mentioned, we're going to have 2 more weeks of lectures after this. Okay. Yeah. So, so we're going to have basically 4 more lectures after this one. Okay, so then I will talk to you guys next week.